उसे पानी की दूसरी बोतल है क्या? किसने पिया हुआ है? Good evening, friends. So today I'm going to speak about the sample storage, preparations, separation sciences, and then chromatographic technique. See, we have done up to now how to we have learned various terminology, then how the analytical chemistry progress it, and then we are looking the sample collection also. So today what we are going to learn is sample preparations, and then after doing the sample preparation you have to do the separation sign. Okay, so the separation, there is various method of separations are there, and in this we will look for this chromatographic techniques also. So before starting these today lectures, I just take a few minutes and then what we had done it my lectures on the Tuesday. So we have a just recap. See what we have learned so far, the analytical terminology. See, if you remember the analytical terminology, what are the some of the most critical point in the analytical terminology is that first you have an understanding of the sample. See, sample consists of a analyte and a matrix. And then the second important point in that is the methodological traceability. See, whenever any number has to be generated, so you have to bring into confidence the number generated by a person by you is a accurate one, okay, or is really represent the concentration of analyte in this. So for that there is a protocols are there how to validate your results. So the validation of the results are done by using a CRM. What is CRM? CRM is nothing but a material which is standardized, already been analyzed, okay, and then a value had been assigned to different analyte in that, and because that number had been generated because that work has been, that analysis has been done by the so many laboratories, and then it has been properly statistically evaluated. That's how this number is assigned for in the reference certified reference material. So the metallurgical traceability, and as far as the chemists are concerned, we are looking for most of the time of the two assay units, either mass in terms of kg, or otherwise we talk about the moles. That is the number, how many moles are present of that particular elements element in that. And then we have seen the importance of this calibration curve. See, whenever any analysis has to be performed. See, analysis has to be performed, then it has to be done by doing a calibration curve. Because as I told you, we learn also that in the, except the gravimetric methods, other instrument does not know what you are doing the analysis. So you have to educate your equipment what you are doing the analysis, and the whatever the intensity of the signal which you are getting it, electrical signal, it correspond to what concentration. For that we have seen we have to do a calibration curve, and then the importance of this is the we have to talk about the sensitivity of that particular equipment. See, sensitivity of the equipment, see whatever the physical measurement which we are doing it, how it is having a affected by variation in the whatever the parameter you have measured in the x-axis. So the variation in the y-axis, smallest variation in the y-axis corresponding to the variation in the x-axis is termed as a calibration slope. Calibration slope. Okay. Then we have seen these apart from this terminology. So there is a then we have learned about the type of the analytical technique. Analytical type of analytical. Then we have seen the various classification of the different analytical techniques. बस ऐसे नहीं चल रहा है आज. Various type of analytical technique, and then here we have seen that the analytical technique had been all the analytical technique had been divided into three category. One is the absolute technique where we does not need any kind of a CRM because they are capable of their own. Okay, and then what is the uh, main benefits of doing the classical method of analysis does not need CRM, and as well as the RSD, which is very important because the relative standard deviation of this is less than 1%. Generally, the RSD in case of absolute methods is about 5.5 to 1%. And then we have seen the relative method. See, in case of a relative methods, we have to prepare, see, as the word say relative, it means that we are doing a relative measurement. So for that, we have to measure we have to prepare a calibration curve by using a standard solution. See, for example, if I am measuring a cadmium in a solution in a water samples, then I have a standards of a various standards solution having a various concentrations. See, I have taken one stock solution. For example, I am having 1,000 ppb of a cadmium solution. So from that 1,000 ppb of cadmium solution, I prepare. Suppose I want to make a calibration curve between the 10 to 100 ppb. So I will have a 10 ppb, 30 ppb, 50 ppb, and 70 and 100 ppb of the standard solution, and I make a calibration curve. And then I will do the analysis of the unknown element, whatever my sample is there. So that's how they call as a relative methods. In this, it's very important that whatever the parameters, whatever the instrumental parameters you are monitoring during the your standard measurement, so you have to maintain the similar parameters in case of a measurement of your samples also. Then comes the comparative methods. See, the difference between the comparative method and the relative method is only that in case of a relative method, we can take a standard material, standard solution of standard solution. But in case of a comparative method, we need a matrix matching standard. See, what are those techniques are there? Like we have said, the neutron activation analysis, whatever measurement we are doing, the XRF. So these are some of the techniques which represent the comparative method. So in this, it's very important that we should have a matrix matching standards. Okay, because if you don't have a matrix matching standard, that calibration curve will not be give a true representation of whatever the measurement is doing is. So, for example, if I am measuring the analysis of a chromium in the steel samples, okay, so I have a standard of a chromium, different chromium concentration in the steel sample only, and with that only I will make a calibration curve, and then I will do the measurement of an unknown sample. So they are termed as a comparative methods. Then we had learned about the solution and stoichiometry. See, stoichiometry is a chemical reaction is very important because any point of time, if you want to know the how many number of moles of particular how much amount of a particular elements is taking part in in the reactions. So whether it is a product, or whether it's a reactant, or any state of a reaction, or a final product. So you must know the stoichiometry of the chemical compound of that particular solutions. And in this, we have seen that the physical state written in the parenthesis while balancing the equation, the physical state always be written in the parenthesis where the coefficient of the variations is written as a coefficients whatever the how many number of for example hydrogen we have seen in case of a methane we need a 4 hydrogen atom in one carbon, so we that 4 has written in the as in a coefficient. Then we have seen how the evaluations from the gravimetry to the calorimetry. See, they are all techniques have a one or others drawbacks are there, and in that few PowerPoint we have seen that whatever the drawbacks are there from one, it has to be avoided by the other, and then how this analytical chemistry progressed from the gravimetry to calorimetry, and finally it led up to the spectrophotometry, and now even we talks about the one atom analysis. We have seen the importance of sampling. See, as I told you, sampling is the central point, because if you had done a wrong sampling, if you have not taken a proper sample, if you have not given an analyst a proper samples, so there is no, whatever the sophisticated or whatever the expert that analyst is that, ultimately is going to get a erroneous results. And what kind of sample? The sample must be homogeneous as well as the representative as well as homogeneous samples, because whatever the sample we are giving, that analyze should be distributed homogeneously with a similar concentration. Suppose if you are having a 10 gram of a sample, and if you are giving it analyst only the 100 milligram of the samples, so the element of X element should have, that X element should be same in that every portion of the sample, in the 10 gram of the sample, and that whatever the elements, whatever the gram you are giving it, it should be representative of that particular that 100 milligram should represent the 10 gram of the samples. So before going, then we have seen it, how to sample the, in case of liquid sample, how the liquid sample will be converted from a dose sample to laboratory samples. And then we talk about this in case of a solid sample also, what kind of precaution has to be taken while doing the solid sampling. And so while taking solid samples, not because we are not talking about the sampling actually. So what kind of precautions taken for the solid samples, and then we have seen the various how to take a gas sample also. So before going to the first lecture, if there is any kind of a queries regarding my first lectures, so I invite, if any one of you have any queries, please put your question in the chat box. We'll wait for 2 minutes for you, and then we'll proceed for the next part. They have a quick question. एक्चुअली में क्या होता है, स्टूडेंट कुछ क्वेश्चन नहीं पूछेंगे तब तक ना अच्छा नहीं लगता है. Okay, friends, if there is no more questions, so we'll proceed for our today's lectures. Okay, see, what is the today lecture we are going to cover it the sample storage, because the last lecture we have seen we have taken the samples, then we have to store the sample because it is not possible that you do the measurement immediately after taking the samples. So sample storage, or even if you are not doing the sampling, it's not possible for you that a sample had come and you had analyzed that sample. So what are the precautions one has to take doing the sample storage? That we termed as a preservation of the sample also. And then from the sample, how to prepare a sample actually. The sample preparation means, see, basically the physical state which you where in which you got the sample, it is not always possible to measure the sample in that physical state, because that instrument will not be for capable of measuring that element in that particular physical state. So you have to bring that you have to do the sample preparation so that you can do the that particular measurement. And then, see, there are many techniques where you need a separation of the analyte, because it is not always possible that all the analysis will be done at a time. So what are the separation techniques are there? So we will see during these lectures what are the how to do the separation of the analyte. And then in the separation of the analyte, today we are going to learn about the chromatographic techniques. Okay, so sample storage. See, okay, so sample storage purpose. So as I told you, there is a time gap between the samples taken and the actual analysis being carried out. So what will happen in during this time? The sample can be adulterated and contaminated by the foreign elements. So during the storage process, if the not proper precaution has been taken, it can be get contaminated. And then, see, because the sample storage, you need a container also. So there is a loss of analyte during analyte also. And how that loss of analyte, it can be get absorbed on the container itself. And then sometimes it's possible that something comes from the container to the sample also. And there are certain cases we will see also that decomposition of the samples. See, during the storage, if you are not maintained, we will see also that, for example, there are certain cases, if we are not maintain the proper temperature, that sample may be decomposed also. And for the liquid samples, see, as far as the liquid sample is concerned, see, it is always necessary. These are some of the things which you can learn through these lectures only, because you may not get these kind of things in a textbook. See, acidic nature of the samples should not be stored in a plastic bottle, because this is one of the because as a matter of convenience, we whenever any sample comes, we keep try to store in a plastic bottle because they are easy to handle. But one should not store if the sample is acidic in nature. If you got an information that your sample is acidic in nature, it should not be stored in a plastic bottles. Because why? Because the acidic acid react with the plastics, and then there a lot of things will get your sample get contaminated. Whereas for the basic liquid samples, it has to be stored in the plastic bottles. Okay. And as far as the solid samples are concerned, see, solid samples are easier to keep and they have a less chance to get adulterated by a. Okay. So sometimes, what will happen, as I told you, it can get absorbed or adsorbed to the walls of the containers. So that is the only precaution you have to take it. As I told you some time back that there is a need for maintain the sample decomposition. So sometimes it's necessary to maintain the temperature. This is, for example, if you are taking the sample of the sulfur dioxide, if you don't maintain the temperature, without flowing reaction get oxidized, and then you will not get any measurement of sulfur dioxide. So to avoid the above reaction in case of sulfur dioxide, it has to be cool it has to be kept at temperature at a 4 degrees centigrade solely. And then the sample should not react with the walls of the containers because again in this case also it get adulterated. Okay, so why the sample has to preserve to avoid decomposition? Precipitation of metals from water samples, loss of water from hygroscopic material, loss of volatile analyte from the water sample. See, loss of analyte for volatile element not only for the water sample, it can be from the solid sample also. For example, you are supposed to do the mercury analysis in the soil samples and you are brought into your laboratory, and then after some time if it not maintain the proper temperatures, okay, the temperature about say about the 15 degrees centigrade temperature, then there will a lot of mercury will be get lost into the into that atmosphere itself. Then how to prepare from the sample which you have collected, how to make a laboratory samples. The laboratory sample is in the form where you can do the measurements actually. So in case of solid sample, usually ground to a suitable particular size to get a homogeneous samples, and then dry the sample because whenever you do the any kind of a measure any kind of a reporting that you have done this kind of measurement or this grams per gram or milligram per gram. For example, if you are taking if you are make any synthetic material into the laboratory, even if you synthetic material is there also one is supposed to measure the moisture content in the samples, because that moisture content vary from time to time and place to place, and so that's why it's very important that you done the reporting on the dry sample only. Dry the samples. For that you have to dry the sample to get rid of it, whatever the water it had absorbed it. And then it's very important because the single analysis, because most of the time whenever you have done any submission of any your manuscript also, so this is the question generally asked by the referee also, whether you have done the single measurement or you are the replicate measurement. So replicate measurement is always necessary as far as possible. See, at least three measurements, three replicate samples should be done before reporting of the any analyte in any kind of a matrix. And what are the replicate samples? Replicate samples are portion of a material of approximately the same size that is carried through an analytical procedure that at the same time and the same way. And obtaining the replicate data on sample improve the quality of the results and provide a measure of their reliability. See, again, before going further, see, whenever there is drinking water samples, see, in case of drinking water samples, so there is because for every kind of analysis, there is a protocols are there. For example, as I told you last time also, see, if you are doing the solid sample measurement, especially when the sample belongs to the environmental in nature, then you have to report it what kind of a particle size are there, what are the range of the particle size are there, whether you have done the measurement in the 200 microns or it's from the less than 2000 microns. So these are the information must be provided with every measurement actually. Similarly, in case of a potable water samples, potable water samples means drinking water samples. So in the drinking water samples, see, sometimes I see, because I assess most of the papers now, people are doing the filtration by using the 0.22 micron. No, it's wrong. Actually, as per the national international protocols, one has to filter the samples to only for the 0.45 micron filter papers. So after doing the 0.45 filtration to the 0.45 micron filter paper only, then only you have to do the analysis of that elements into the water samples. And what will happen what are the sources of error in this case? See that incomplete filtration, and sometimes your element of interest will be get absorbed on the filter paper. So one has to taken care. So that's why you how to avoid those things, the loss of element due to substance on the filter paper. So you have to wash the filter paper thoroughly by using the deionized water. Then, in case of a solid samples, see, in case of solid sample, because most of the time it is not possible. See, if I'm doing the measurement by using the XRF, then I can do the analysis by using the solid sample also. But solid sample and the XRF, as you may be knowing, is having its own limitations, because I cannot go up to the in the range of a ppm. If my analyte of interest in the percentage levels, then only I can perform this XRF analysis. But most of the time, the solid sample has to bring into the solution form. So that's why a perfect solvent has to be chosen, the perfect chemistry has to be chosen, by which you can bring out all your element, element of interest, or all the analyte whatever you are interested, whatever analyte you are interested to bring into the solution form. So that's why you have to choose you have to choose a solvent which will decompose the analyte, or which can take selectively that analyte in that thing. See, most of the time we do the complete digestion in case of solid samples. That also we'll see then in the next PowerPoint, how to completely convert the solid into water. And what are what are the sources of error here? Incomplete dissolution of the analyte, loss of analyte by volatilizations, introduction of a analyte as a solvent contamination, because many times your solvent, if you measure, for example, if you are doing the in the measurement in the range of a ppb, then there is a contamination due to solvent, has to be avoided, and actually we use the extra pure chemical, ultra pure chemical actually in that case. And the cost of the ultra pure chemicals is almost tenfold than compared to the whatever the AR or LR grade chemicals are available into the market. And then, because you are doing all this processing in a container, so the contamination from the reactions of the solvent with the vessels falls. Also, these possibilities are there, because there some of the contaminant come from the vessels walls. Then what are the technique why we do these processes? That can be done by using the dry ashing, wet ashing, and that can be performed by using wet ashing can be done by using is a conventional hot plate, and microwave also, that we'll see in the next few PowerPoint. And then the last resort is our fusion. So first we will take the dry ashing. The simple dry ashing performed by, you just weigh the sample in the crucible, heat in a muffled furnace, and then this residue is dissolved in a suitable acids. And what are the temperature range where we do this ashing is about 450 to 550 degrees centigrade. And we used to add magnesium nitrate, is commonly added just to accelerate your process of ashing actually. And suppose if your sample is a very highly organic in nature, then you just do not put your sample simply in the muffled furnace, because otherwise there is a lot of black fumes will be there, and then all your if it is not properly ventilated, that room will be getting suffocated. So for that, what we do before putting the sample into the furnace, we do the open charring. Okay, so that means that we'll burn the samples into the open flame, and then only we'll put into the furnace. But in this case, if you are doing if you are interested in doing the analysis of the mercury or arsenic or lead, then this thing, is not possible to perform this kind of dry ashing, because then it has to be done by the microwave digestion only, because these elements will be just getting evaporated. And generally, why has to be done? One has to do this ashing actually, because whatever this, we are going to see whether it's a wet ashing or a dry ashing. Why one has to do it? Because most of the time, all the organic materials, they will, it's not possible to do the complete inorganic analysis in the presence of organic substance, because once you put in the acid in that, some gelatinous precipitate, we will get it, and then whole your analyte will be get absorbed into that one. You cannot aspire either in ICP-OS or AAS or ICP-MS, or even you cannot do the UV visible you cannot do the measurement by using the UV visible spectrophotometer also. So those care has to be taken. just to destroy all the organic substance before doing the organic analysis must. And for that purpose only all this ashing has been done. Then this dry ashing, if these samples are suppose if you have to perform this dry ashing in case of liquid and a wet tissue, what one has to do is that you has to completely evaporate the sample before putting into the muffle furnace. And then after doing this completely drying of the sample, you will put in the furnace, and then again it will dissolve in a smaller amount of acid. It will be very nicely getting dissolved, and then you can perform the analysis. What are the advantages of doing the dry ashing? The ability to decompose a large sample size, because you can take a even 100 milligrams, 100 gram, or even 500 grams of the sample and do the ashing if your muffle furnace is big enough. Then because once you perform the ashing, then the reagent requirement always reduced by 1/10, and this technique is relatively safe. The ability to prepare a sample containing volatile combustion elements such as sulfur, fluorine, and chlorine. If we have to do it, then we have to use the Schoniger's oxygen flask combustion technique, which is very popular in this case. And the technique lends itself to a mass productions. And what are the disadvantages of doing this dry ashing? Because losses due to retentions to the ashing container. Then there are losses may be due to the volatilization, contamination from the ashing containers, contamination even from the muffle furnace, and the physical loss of a low density ashes. Because once you open once your material is, because if somebody had performed these ashing things, or even if you heat the elements in muffle furnace, you have seen that once you open the muffle furnace, because if it is very low density, because then a lot of ash will come out of this. So it means that you are losing your analyte in that, so you will not get a proper results. And in case of certain difficulty in dissolving certain metal oxides, because it's not possible to dissolve those metal oxide, then once they ash it, and formation of toxic gases in a poorly ventilated room, because your area should be properly ventilated. Your muffle furnace should be kept in a fume hood, which having a proper ventilations. So these are the few, example of doing the wet ashing. You'll see that usually use the combination of acid. Generally, we use the HCl and HNO3, and sometimes only we use the hydrochloric acid, performed in different kind of vessels depending upon the combination of acid. And boil of acid evolve the white fume. This kind of white fumes you see that at the end of the process. So as I told you, they usually use a combination of acid, that's HNO3 and HCl. But if some silicate is present, then in that case you have to add the HF, okay, to decompose the silicate, because otherwise the silicate will not decompose. Because this is one of my favorite question I used to ask the student: how you can convert this 100 milligram of a soil into water samples, into water, okay? So this is how because by using the HF, you will completely destroy the silicate matrix, and all your material will be converted into a solution forms. And generally, sometime only we use the perchloric acid. Also, again, perchloric acid is again used to accelerate the decomposition of the organic complexes. And sometime only we add a few drops of or suppose if it is a higher amount, then you get a 5 ml of H2SO4 is added. And what is the because HNO3 destroys the bulk of the organic material, but it does not get hot enough to destroy the last traces. And it is boiled off during the digestion process until only H2SO4 remains, because once the temperature goes, only because the boiling point of the H2SO4 is quite high than compared to the HNO3. So HNO3 goes off and only H2SO4 remains. And once the H2SO4 you heat it, so the white fume, whatever the white fume you have seen in the last PowerPoint, that's so the sulfur trioxide fumes are evolved and begin to reflect in the flask. At this point, the solution gets very hot, and the remaining organic material we can destroy it, because there is many organic compound, they can decompose at a various temperatures only. So that's how we need an addition of a sulfuric acid also some. And what, what are the advantages and disadvantages of doing the wet digestion? Superior in terms of rapidity. Okay, definitely, because in a muffled furnace we have to wait it for 4 or 5 hours, and where it can be done in a 1 or 2 hours. Low level of temperature maintained because we don't need to go to 450 degree or 500 degree centigrade, and freedom for loss fire retention. What are disadvantages are there? Because disadvantage only because we are using so many solvents are using, so introduction of impurity from the region necessary for the reactions. Then, as I told you in the beginning, before some PowerPoint, this wet digestion can be done in the on a normal conventional hot plate or even in a Bunsen burner. But there is alternate are there. Suppose if some cases, if this wet digestion can be performed in the microwave digestion, what are the advantages of using the microwave digestion? Because we can vary the pressure. Once you can vary the pressure, you can cook, because instead of 1 atmospheric pressure, we can institute 10 bar or 20 bar. And then it will give us freedom that we can increase the temperatures from the, not from the 100 degrees centigrade, it can be increased up to 50 degrees centigrade. So the microwave digestion system can be programmed for a proper pressure, and then a temperatures gradient will be given through which it will be elevated up to 50 degrees centigrade. And the other important thing is that because it has to be done in a very closed vessels only, this is, specially designed vessels are available for doing the microwave digestions. And the advantage for this is that, whatever the volatile elements are there, so they will not be getting out of the system, and it can be this sample can be analyzed even for the volatile element. The wet digestion can be performed even for the volatile element, because you need a very less amount of acid than compared to the open digestions. So therefore, there's a low blank, means the possibility of adding impurity to the solvent is also less, because the less amount of reagent has been used while performing this thing. Okay, so this I think you most of the people may be knowing. See, what is the why the microwave digestions are faster? Because here we are not using the conventional method of heating, that is not conductions. Here the microwave energy directly transferred to the molecules, and it will raise the the temperatures for whole the bulk in a very faster way. And as I already told, the further advantage, decomposition type of this type is loss of volatile component of sample is virtually eliminated because the vessel is a closed one. The last resource, whenever this neither my dry etching help nor my wet digestion help or nor microwave digestion, then we have to perform the fusion. See, fusion is the last resort, and the analytical chemists use it at the last only when the samples, because there are certain type of inorganic sample which is very unreactive for the acid decomposition. So those reactions, to bring that analyte of interest into the solution, we have to perform the fusion. So there are the various fusion mixtures are available, and so as I told you, fusion are considered to be more of a last resort by a trace analyst, because they are expensive and often not available, because high purity fluxes are not available, because this flux itself will add a lot of impurity into the sample, and they yield in high solid solutions, because see, most of the time, the sample had been analyzed by using the ICP-OS or ICP-S or ICP-MS. So once you are having very the solid concentration, means salt content is very high in your samples. So what they do, they choke the nebulizers. Of course, there is some special nebulizer, that is Miramax nebulizers are there, which is meant for the solid solution having a high solid content can be used. But generally, we avoid it because until necessary, then only we do the fusion. And then larger dilution of the sample is necessary. And definitely, there is a lot of spectral interferences from the fluxes or crucible construction material must be considered. And contamination of the sample with the crucible's construction element and impurity must be considered, and it's really a labor intensive one. Now, up to now we have seen this analytical chemistry, which is of most of say synthetic in nature. So generally, being an environmentalist, I always, the way to distinguish the difference between the normal analytical chemistry and the environmental analytical chemistry. So, as the definition says, both the place the definition is same only. Okay, so here also we do the sample processing, separations, identification, and quantification. See, in case of a normal analytical chemistry, this is natural or synthetic origins, where in case of of environmental importance. So, what is the difference of these two kind of environmental analytical chemistry, normal analytical chemistry? See, in case of in environmental analytical chemistry, see, we generally talks about only the either in the range of a ppm or ppb only. And in case of some emerging pollutant, like now we speak to a lot of nanomaterials also, because there are a lot of nanomaterials which, of course, in India still we don't have a regulations about the level of nanomaterials in the different environmental matrices. See, lead is present as a not in the nano form, but lead is present as an element also in the soil sample. But lead may be present as a nano form also. And you know that the hazard of lead in the nano form is much more rigorous than compared to the its normal form. So there are regulations are coming for this. In US, of course, these regulations are existing, but I think in India also it will come very soon. The concentration of the nanomaterial in the environment. So the basic difference between normal analytical chemistry and the environmental analytical chemistry only, because in the normal analytical chemistry either we talk in the percentage, molarity or normality most of the time. Whereas in environmental analytical chemistry, we only talks about the ppm or ppb, means microgram per gram or nanogram per gram. And of course, as I told you, many of the emerging pollutants, even if we go to the PPT range also. See, the environmental matrices are diverse in natures, detecting these levels of, because now what is most important in that? See, you have to bring out that small concentration, means the PPV range or the ppm range of the elements into a form where you can measure it, and then you have to bring that element, to extract that element from that complex matrix actually. Okay, see, suppose if you are taking the 1 gram of the sample or 10 gram of the samples, so out of 10 gram of the sample, you have to remove it only that ppb of the sample out of that. It's a really a very tedious one, because you don't know while using this solvent whether you are added due to the solvent which you are using for the extracting that element, or because of that it is naturally present in that element. So it's a very tedious one. So detecting a trace level of environmental pollutant from complex material require a complex and a tedious procedure to remove interferences, background, bulk chemicals. See, bulk chemicals, there is backgrounds are there from the bulk chemicals actually. So we have to remove those interferences and separate chemicals of interest, constantly allocate to the detectable labels, so that you can easily detect whatever the instrument is available to you. So, not only instrumental analysis is essential, but also the sample preparation is critical for the expected accuracy and precision of the entire procedure in case of a environmental analytical chemistry. And many times the sample preparation at the critical component of the uncertainty and variability toward the overall environmental measurements. Now, I am going to shift to the next portion of my lectures. Again, I will give you 2 minutes. If you are having any queries, please, I will be very happy to answer you. And I'm sure that if I'm not able to answer you, I will definitely find out the reason, I'll go back and then look for your answers. And yesterday somebody asked me two very relevant questions, this absurd and ruggedness. But then I go and back and check it. So whatever answer I had given it, they are very correct one, because as I told you, I taken more than 600 lectures, but so far nobody had asked me these questions. So if any questions in your mind, even if you are not an analytical chemist or you are not doing any work of chemistry, in general also, because today we talk about something very, normal day-to-day chemistry things which you are facing into the laboratory or even in your day-to-day life also. Any queries or any questions are there? Please come forward. Kavishika, you are here or you are just keep it on? Hello, Kavishika? See, as I told you, why you see before doing the any kind of a analysis, one has to perform the analytical separations. Okay, and this requires the many chemical analysis are not specific for one compound. Actually, respond to many potential interference in the sample, and often it is necessary to first verify the compound of interest Why to remove? Because removing the interference, because in a few PowerPoint you will see that what I am talking it in this PowerPoint. Okay, so separation step. And sometimes we need, pre-concentration step also, because pre-concentration is necessary, because suppose if you are having there are two reasons: either the concentration of the analyte is very, very low, but still you want to know the concentration, then you need a pre-concentration step. And second, because the availability of the instrument, for example, in your lab, you don't have a ICP-OS or ICP-MS or even AS, then you can't do the analysis in a very, low ppm range or a ppb range, low ppm range. You forget about ppb, ppm range. So for in that case, you have to do the concentration, because you have to produce the result, and still you have to measure the concentration. So that's how you need a pre-concentration. So what are the different methods of this separation methods are there? One is the solvent extraction, which you might have read from even from your 12th class also. Ion exchange also, ion exchange chromatography. Ion exchange also we have done, you might have done some of the experiment in your 12th class, or even in your BSc, even if you are having a subsidiary subject as a chemistry. And then chromatography. So we will see one by one all these separation methods. See the solvent extraction. The solvent extraction, what is the solvent extraction? Solvent extraction, the distribution of a species between two phases, and one of them is usually aqueous and the other is a immiscible organic phases. Okay, so what you'll do, that solid phase will be getting distributed in these two phases, and the partition of the solid is between the two chemical phases, and is described as the equilibrium constant, as is called as a K, where the ratio of the concentration in the two phases is called as a partition coefficient. Okay, so generally we use in a solvent where the partition coefficient is very high, very high. Okay, so now we see in this case of examples. For this I am taking, I am trying to make you to understand what is the importance of the importance of the solvent extraction, and how we can remove, we can do the analysis of a trace element even in the presence of the bulk material. So for this, we are taking the example of the uranium. See, in case of a uranium sample, I have to do the analysis of the trace element like iron, aluminum, zinc, and other elements which are present in the traces. Whereas the uranium is present as a bulk material, because my uranium is more than 99%. So what I will do that, still I have to perform the analysis. So in case of this, if I dissolve the uranium sample in HNO3, I can dissolve it, but I will not get any result because of due to the spectral interference. So until unless I remove the bulk of the matrix, in this case is uranium. So how I am doing it? Performing this analysis, I am using using a method of solvent extraction. So by using the solvent extraction, what I am trying to do it, I remove the uranium, the total uranium I will remove from that bulk material, and then do the analysis of this thing. So how I will proceed it? So for this, I will use a solution uranium tributyl phosphate and a water sample. So tributyl phosphate here is basically we are using in the kerosene only this tributyl phosphate, just to reduce the concentration, or because it's very expensive one, and a water layers. So whatever the elements, whatever this uranium will there, it will form a complex of uranyl nitrate, and it will sit in the tributyl phosphates. Okay, and then whatever the trace elements are there, they are the water soluble, so they will come in the water samples. So after doing this solvent extraction, I will take the whatever the water is there, so I will take out the water and then perform the analysis of the trace element in the uranium samples. Like that, there are so many, chelates are there, because here also what the TVP is doing, that it taking a uranium by using these ion dipole interactions. So there are many chelates are there. They are some of the common example, that is cuprophorone, 8-hydroxyquinoline, dithiogen, crown ethers, and then this is basically work on this host gas interaction. And what will happen in this metal ion, that is, this metal ion is extracted in the central cavity of that particular chelating chelates or a polyfunctional organic base. And that's how I get separated out this one. Then comes this ion exchange. So in case of ion exchange also is a very simple one. See, it's a basic, what is the ion exchange? So it's a reversible exchange of ions between a solid and a liquid in contact with it. See, ion exchange, you are taking any liquid samples. So this is a reversible exchange of ions between a solid and a liquid in contact with it. So what is solid in this case is my resin. So generally resins is prepared by using the either of a styrene divinyl benzenes. So this is called a example of given of a styrene and divinyl benzene. This is styrene divinyl benzene. Resins of styrene divinyl benzene is there. Then it will be properly, because it can be of the cation exchange, or whether or you want to do the cation exchange or you want to do the anion exchange. So similarly, you can functionalize it either by using different functional ions like that. You can make it the anion exchanges and the cation exchanges. So what are the various anion exchanges? Quaternary ammonium group, alkylamines, hydroxyalkylamines, alkylamines with the acrylate type of cross linking, whereas the cation exchanges can be.
कौशिक म्यूट किया था, उसके वजह से आवाज आ रहा।
अच्छा, ओके, स्टार्ट फ्रॉम। Okay, so you can see that you can either functionalize by the anion exchanger or the cation exchanger, or what are the different kind of a substrate you can use for making the region is a polystyrene divinyl benzenes, polymeth acrylate, polyalcohol, and hydroxyethyl meth acrylate, that is called termed as a HEMA. So the principle of the this ion exchange is preference for ions of preference for oils of particular type is often expressed as through an equilibrium relationship, that is the selectivity coefficient. So what is the selectivity coefficient? Basically for the exchange of A positive ions in the solution with a B positive ion. This is basically, we are given an example of the cation exchange, and the bar terms indicate location on the regions where the bar, this is called the bar terms, indicate location on the regions as a region phase as opposed to the solution phase. So this is how the selectivity coefficient is defined and given. So what are the factors on which the selectivity coefficient depend? The factor which affect the selectivity coefficients for a given region. For example, if I am using styrene divinyl benzene regions, so for a given region, ion selectivity is a function of this ionic potential. What is the ionic potential? Basically nothing but say ionic charge versus the hydrated radius. I hope that everybody will understand the difference between normal radius and a hydrated radius, because when say any ions is present into the solutions, we always talk about the hydrated radius only. And a functional group and ion chemical interactions. So these are the the region of the selectivity. In most cases, the higher the ionic charge, the higher the affinity. Smaller the hydrated radius of the ion, the greater the affinity. So it depends both if the ionic charge is higher, this affinity is more. Even if the hydrated radius is low, then also is having the higher affinity. Now we talk about this chromatography. So chromatography, see, chromatography is defined as a procedure by which solutes are separated by a dynamic differential migration process. How they are separated? Dynamic differential migration process in a system consisting of two or more phases and one of which is move continuously in a given directions, and in which the individual substance exhibit different mobility by a region of difference in adsorptions, partitions, solubility, vapor pressure, molecular size, or ionic charge density. Because on that basis, there is various kind of chromatography techniques are there, and that we will see one by one. See, what are the important terminology when we talk about the chromatography? One is the mobile phase, stationary phase, and then band or zones. So, what is the mobile phase? The mobile phase that travel through the column, that it transport a sample through the column. Stationary phase, immiscible solid or a liquid phase that fixed in place in a column or on a solid support system, retain annulate within the column. And then band and zone. So these are basically, the band and zone. Area which annulate is distributed on column, and zone of a different annulate gradually separate as band progressively down the column. So these are the basically three more important. See, whatever the kind of a chromatography are there, we talks about the mobile phase, stationary phase, and then band or zone. Of course, their names are changing as per the techniques are there. So the various classification of the methods in chromatography, there are two broad classifications schemes are there. That is mobile phase. Either they will be vary because of the mobile phase or the attractive phase. Now we will see one by one what is the difference between what are the variations due to the mobile phase and what are the variations due to the attractive forces. ये इधर से क्यों नहीं चलता है? ठीक है, हाँ. Okay, so the mobile phase, it can be a gas or a waters or organic solvent or a supercritical fluid. So for your clarity, I already given the definition of what is meant by the supercritical fluid and then supercritical chromatography. So in case of a gas chromatography, we are having a gas solid and a gas liquid. So what will happen in case of a gas solid? The mobile phase is a chemically inert gas, and that serves to carry the molecules of the annulate through the heated column. And what is the stationary phase? The stationary phase is either a solid adsorbent, which will be termed as a gas solid chromatography, or a liquid on an inert support termed as a gas liquid chromatography. See, this is very important to know that a liquid on the inert support. So it's not basically it's inert support only, but the molecules, liquid molecules are attached on that solid supports. And then see, one of the most unique characteristics of this gas chromatography is that is the only sole form of chromatography that does not utilize the mobile phase for interacting with the annulate. So this is the only one unique feature of this gas chromatography, where the mobile phase does not interact with the annulate. Whereas the liquid chromatography can be based on a column where the flow is due to the gravity flow. We can use the pressure that we call the HPLC, high performance chromatography. And it's in case of a simple column chromatography, we can use this principle based on the adsorption. So these are the classification based on the mobile phase. Then the classification can be also be done on the basis of attractive forces. The attractive forces may be adsorptions, ion exchange, partitions, and a size exclusion. So what will happen in case of a adsorption chromatography is based on the principle that some solid substances which are known as adsorbent have the power to hold the molecule at the surface. And this holding process is due to that's what is shown in here in this diagram, that a solid molecule and the solvents are there. And you can see that the solvents, the molecules are held up on that stationary phase. The holding force is due to weak non-ionic attractive force of the like van der Waals or a hydrogen bonding, which only occur at a specific adsorption bands. And separation based on their adsorption on the surface of a solid, that is a stationary phase. And in case of a normal phase, like separations, we have a non-polar mobile phase. And for a polar non-ionic compound, normal phase like separation means non-polar. Your mobile phase is non-polar, and for a polar non-ionic compounds, And in normal phase chromatography, the stationary phase is a polar, usually using a silica, which contains the SiOH group, and the mobile phase is non-polar using hexanes or a chloroform. And then compound with the greater affinity of polarity eluted later in the chromatograph, and those with the less polarity elute earlier. So this is the basis of their separations. The compound with the greater polarity, they elute later in the chromatograph, and those with the least polarity, they will elute earlier. Then in case of partition chromatography, the solutes are separated based on their partition between a liquid mobile phase and a liquid stationary phase. We have seen that how the liquid phase is coated on a solid support. In case of normal, analyte is a non-polar organic, and stationary phase is a more polar than the mobile phase. So in case of a normal partition chromatography, analyte is a non-polar organic, whereas the stationary phase is a more polar than the mobile phase. Whereas in the case of a reverse partition chromatography, analyte is a polar organic compound, and the stationary phase is less polar than the mobile phase. Examples are these thin layer chromatographies or the paper chromatography. Then ion exchange chromatography use ionic stationary phase. Ions separated on the basis of their tendency to displace counter ions and adsorb on the stationary phase depend on charge, where it depend charge, hydration, solubility, and used for the analysis of it's used for the analysis of amino acids and its base pair. Anionic stationary phase used for the cation separation. Cationic stationary phase used for the anionic separations and used for the ionic compounds only. So these are the example is shown the ion exchange, and then this example is shown for the cation exchange. Then the size exclusion chromatography. As the word says, size exclusion chromatography. Here separations are possible because of we are using the resins having a different kind of a pore size. I don't know whether you have heard any XAD4, XAD7, XAD8. Different kind of XADs are there depending on the pores are there. So here the separation is a result of trapping of a molecule and the pores of the packing materials. Very large molecules cannot go into the spores, so they will be retained, unretained, and they come out. And very small molecule get hung into the pores for a long time, and then it will be removed from that pores by using the various solvents are there. And the best example, if anybody is working with a humus material, so uric acid generally how we separated in case of a liquid sample, we are using the conditions or XAD column condition with the sodium hydroxide XAD column for trapping these humic molecules are there. So that's how we do the separation by using this is the use of the size exclusion chromatography. And here what is the stationary phase is the porous materials having different pore size. So this is how the different chromatographies are there. We will see example in the next PowerPoints. Liquid chromatography. Separate liquid sample with a liquid solvent, that is mobile phase, and a column composed of a solid bead is stationary phase. Gas chromatography. Separate vaporized sample with a carrier gas. The carrier gas is a mobile phase, and a column composed of a liquid or of a solid bead, that is termed stationary phase here. Because sometimes, as I told you, that stationary phase, that liquid will hold on the stationary phase. And paper chromatography, separate dry liquid samples with a liquid solvent and a paper strip. Because this paper chromatography, I think all of us had viewed in our 12th class for separation of the various amino acids actually. Then thin layer chromatography, separate dried liquid sample with a liquid solvent. It's a mobile phase, and a glass plate covered with a thin layer of alumina or a silica gel that is coated on that glass plate, that termed as a stationary phase. So in case stationary phase varies as per the type of chromatography. In case of a paper chromatography, we are having the stationary phase either a filter paper or cellulose. Thin layer chromatography, we are using a silica gel. and aluminum polyamide, because generally you can coat that glass plate with the silica gel or make a column of the silica gel or alumina or a polyamide. Gas chromatography, we can use either Skillet and Epizone, Carbovex SEM. High performance chromatography, we having column of various columns are there basically. So some of the columns material I written it's C8, C18 and Licosorb and silicones. Similarly, in case of mobile phase, paper chromatography, generally the air or alcohol. Thin layer chromatography can be a mobile phase, can be by hexene, ether petroleum, or alcohol. In case of gas chromatography, we can use either helium, argon, and nitrogen. See, this is one important point is that all of them are other inert gases are there. So that's why I told you one of the unique advantages of the case of gas chromatography that your analyte does not interact with the mobile phase. Then high performance liquid chromatography, the cyclohexene and hexenes, carbon tetrachloride, ethanol, methanols, and even air also. So we'll see that now in some details about this paper chromatography. I just need 2 minute break. Okay, so in the next few PowerPoint, we read about this paper chromatography, and then we'll define these, how these RF factor is defined in case of a chromatography, because one of the important thing and many questions comes on this about this retention factors. So as the definition of the paper chromatography, analytical separation technique for complex mixture involving the progressive adsorptions of the dissolved component, and that has to be done on a special grade of a paper. It's not a simple, better not to take a simple cellulose type of paper. The certain solvents are used to separate for example, the water and alcohol. With capillary action, the solvent will move up to the filter, and the movement of a solvent will bring together component that are separated from the mixtures. Every component that are separated will move to a different velocity, and that we can see that the moving component depend on the movement of the component, that analytic component depend on the solubility of a solute in a solvent, intermolecular forces, and pore size of a filter vapors, and size of a solute. At the end of process, component that are separated will be immersed to a different distance on the filter vapors, and then how this retention type or retention factor values are used to identify identification of each components, and this is how we define it. The retention factors or RF is defined as the distance traveled by compound divided by the distance traveled by the solvent. So you can see in that particular diagram, see this is the solvent front, and then these are the compound which is from the new position of this, for example, your solutes. So distance traveled by the compound divided by the distance traveled by the solvent. So distance traveled by the solvent is 2.8 centimeter, whereas the distance traveled by the compound is only 2.1. So the retention factors comes out to be 0.75. So this is how the various retention factors actually make. These retention factors are basically in return is a fingerprints also for the separation of the different compounds. So this is basically a block diagram as shown in case of a mobile face. See, before going further, these all chromatographies needs a few lectures. Each chromatography technique need a few lectures. But since during this 6 lecture course, I'm giving just a glimpses of all the type of technique, so that you are aware whenever you are going to use because you are going a different multidisciplinary research. So, whenever you need what kind of analysis has to, whatever your requirements are there, so accordingly you can approach the various analysts, or even if you are in, if you are interested in the analytical chemistry, then definitely you come back to me. We'll teach you in details, and then even we can talk on this thing on the my mail also. So this is basically instrumentation of the HPLC. So it's not that simple block diagram, because there is a various kind of a detectors are attached with the HPLC. Of course, the solvent system, the mobile phase reservoir pump and the sample injection in the column, they are more or less similar only, the same type only. But that it depends on the what kind of detector, because on the basis of detector, the capability of the HPLC will vary. So these are the various kind of HPLC detectors. Detectors, that is, we can use the refracting index where the sensitivity is quite low, with 100,000 nanograms per ml. We can use the conductometry, which is having a sensitivity of 100 nanogram per ml, whereas the UV visible is about 10 and mass spectrometry 0.1. And the best and excellent one is a fluorescence detector, which attached with the HPLC, we can have a selectivity of 0.001 nanogram per ml. So you can ask this type of question: why go for such a low level of detection sensitivity? You need it. See, if you are looking for some organic contaminant in various food products, they are in a very, very low levels, but they are dangerous actually. They are not good for a human health. So there we need a detection up to that low levels actually. And even in case of some kind of drug formulations also, they mix they while they're performing the drug, they need a very, 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 very small quantity. So they using that either mass spectrometry or fluorescence detector with the HPLC while performing the quality assurance on that particular drugs. And similarly here also you need a calibration curve. So whenever you're doing performing any see, we can do the qualitative analysis as well as the quantitative analysis by using the HPLC. And then here again you have to prepare a calibration curve. Okay, so by using the external standard. So there we have shown the example that we have 100 nanogram per ml to the 5 nanogram per ml, and then after making that curve, calibration curve, you can put your unknown sample, and wherever you are getting the peak height. So with the peak height, you will know the concentration of your element present in your unknown samples are there. See, one thing, you may be very surprising. See, whenever a sample is given to you, see, the analyst must be knowing which analyte you are interested. See, suppose if I do not know what analyte you are interested, I cannot prepare a calibration curve. And then I do not know why this genuine question does not come into your mind. Suppose if I get an unknown samples, then how I will proceed it? There are ways for doing that one, because you will run a GCMS type of thing, and then you can see what kind of various possibilities are there, what kind of different kind of analyte to be present in your samples. Then accordingly you have to each pinned to done then element to element or compound to compound analysis. Then comes this gas chromatography. Gas chromatography has been a very wide application and been used very wider application of this gas chromatography. So what this is instrumentation that it contain a gas supply system which is a carrier gas. Flow controls are there, injections, because here is basically everything in a oven. Because the moment you introduce your sample, it has to be, because most of it you are having a liquid sample. So the moment you convert, we put your sample here, it will be converted into a vapors. Then there is a different kind of columns are there for this gas chromatography. So what are those columns are there? So there's a packed columns or a open tubular columns are there. Okay, so the case of packed column, they are having 3 to 6 diameters and tubing about 1 to 5 meter long. Okay, circle it and used for the preparative separations or to separate gases that are poorly retained. Lower resolutions are there because of using this packed column, and small uniform particles size decrease at diffusion and requiring a higher pressures. Whereas the open tubular, which is more common, having a inner diameters of 0.15 to 0.5, and they even long for the 100 to 10 to 100 meter long, and zero point 0.1 to 0.5 micron thick special coatings on the nervous, and the higher resolution, shorter analysis times, greater sensitivity compared to the packed columns are obtained when we are using the open tubular columns. And this is the one of the most common. There again in the gas chromatography also there is possible of having a different kind of detector, but the most common detector used is the FID, that is flame ionization detector. So whatever you do it, what this flame ionization detector do? See here the organic solute, whatever the organic solutes are burned into the flame and producing these formyl radicals. This is how the generation of the formyl radicals are there in detectors. And then these formyl ions are collected by the cathode and produce a current, because there is a anode and a cathodes are there. So whatever the electrical signal which we are generating, electrical signal will be generated, and then it has been recorded. That's how the concentration of this analyte has been determined. So again, in case of application, what are the various applications you can do? The qualitative analysis as well as the quantitative analysis. As I told you, qualitative analysis only you will know that this kind of elements or compounds are present. Elements are present, and quantitative you can tell the concentration, how much amount is present. Then the identification of the compound is again based on the retention time comparison, because most of the all the chromatography techniques are based on the retention time comparison. Okay, so this has shown this is unknown sample and a known one. Then in gas chromatography, one of the pyrolysis gas chromatography. Pyrolysis, as the name says, that here the temperature is very high, that we are doing the performing the pyrolysis. And what for the use is used for the identification of the non-volatile material like plastic, natural and synthetic polymers, and some microbiological material. Again, it is based on the fingerprint chromatogram for the sample, which result from its thermal decomposition and fragmentations. And aspects of the GC application is mostly the food analysis. Analysis of food is concerned with the confirm the presence and determination of quantity of analytes like lipids, proteins, carbohydrates, preservatives, flavors, colorants, and also vitamins, steroids, and pesticide residues. Again, here is again, it's very important that if you are doing any kind of analysis, you have a perfect CRM also for those things. If you don't have a certified substance material of those thing, you you can measure it, but you cannot perform with the you cannot done the validation of your data. You cannot submit result with the proper authenticity. Then drug analysis. This is widely used to identification of the active component, possible impurity, as well as the metabolite in the various kind of a drug. Environmental analysis, environmental contaminants like dichlorophenils, like chloroethylene, that is DDT, and the polychlorinated biphenyls, PCBs, are present in the environment at very low concentration and used for, GC is very frequently used for the determination because its sensitivity and separation power is very high for these compounds. Forensic analysis also, GC is having wider application, and because we need a very small amount of samples is required for the GC analysis. And again, because of its high sensitivity and separation efficiency, this is used in the forensic analysis also. Because you may be knowing that, many of the results will be that like saliva and others, body parts, body fluids analysis has been done by using GC only. And it's very helpful by the police to to generate the crime scene. And use of paper chromatography, separation of ink dyes to compare ink dyes used in a company. Food coloring, differentiate color agent used in the food product. Then various botanists and herbalists also use the paper chromatography to isolate plain pigment from the roots and leaves. Okay, so with this, we are going to finish the today lectures. But again, my same request to you, because it's not possible for you to understand everything. Even if you are having any kind of a question, even if you are doing any kind of analysis concerning of the today work, either you are using HPLC, GC, or paper chromatography, or GCMS, if you are having any queries regarding those things, if you are facing any kind of problem, please come out and then raise the question, so we'll try to answer it. And I'm sure that the first part is very important, that is how to do the sample preparation, see dry hashing, wet hashing, and even in case of fusion also, sometimes we need a fusion, and then this wet hashing is prepared by using the either microwave or a normal conventional hot plate.